series. So you basically, let's say if you want to, this is a MOSFET. MOSFET is a bidirectional device, right? MOSFET can switch back and forth. IGBT and BJT can only switch in one direction, right? So you can basically put a diode, the same diode in series with the switch to include directionality. And let's look at the diode. So diode, we have a circuit file. So this diode is, we have certain parameters defined, and then we also have a snubber included in this diode, which is a resistance of 10 ohms and capacitance of 100 nanofarad. So this diode includes an inbuilt R and C, and then we have this particular model power diode, which we perturb with CGO values, FF values, NIS values, and RS values. Okay, so, and then we also have within, well, this is the amplifier model from ST Microelectronics. So if you want to look at this model, I guess it is.
You try what part?
Yeah, I think. Let me do this. By the way, this is how your CD is structured. In the CD, you have got demos. You have 25 demos, and you have got part 2 BLDC, then 3 AC inverters, 4 induction motor drives, 5 DC-DC converters, 6 stability analysis, and 7 power met connections. So those are the demos you have on your CD.
With all the schematic files?
Yes. Yeah, and if you need, we can email you the net list. If you just want a net list, we can email you the net list, and so you can use on any other SPICE program you want to use. So here we have got the text file. So let me see if I can open this text file. WordPad, is that what you said? Yeah. Okay. So you can see the model is quite complicated, and it is a macro model, and you can see how deep it goes, and you can see how many parameters have been defined and how many models. These are all the parameters. So it's quite adds significant complexity to your simulation. So you can, I mean, eventually you can begin to incorporate once you have got a stable simulation model. Okay, so back to this, we have, and the PWM also, we have the PWM circuit, which is this circuit here. It's got a gate drive plus, gate drive minus, and duty cycle. And here you have got E source, and the value is basically that same function we had discussed in a cost and a cost function. And then you have a second E source, which basically based on tan hyperbolic function, right? So that's your PWM. And let's while we are here, let's look at the last file is the parameter file. So this is how I'm sure you can improve on the organization, but this is basically the whole text file where we have all the parameters. and at the bottom you have the switching frequency here, and the rotational frequency is up here. Okay. All right. So this is what we have now. So this is your page 1 of the schematic. Now, using AND gates is not the smartest thing here. You can also use essentially simple switches. So the switches turn on when you get AT command, because this one turns on the digital simulation part of PSpice, and the simulation is much better if you don't have to use the digital part of PSpice. So I think you have seen, this is a standard gain block from PSpice. It just multiplies high feedback with 1,000. Essentially, this is 1 milliohm resistor, 4.7 and 4.7 microfarad. So the time constant here is such that it's about, let's say, 25 microseconds. And so if you take 5 times that, your switching frequency is 50 microseconds. So you probably could increase this a little bit, but 25 times 5 is 125 microseconds. So you're trying to average out over 2 periods. We look at schematic 2. This is how we have got the motor. You can see. Now these are the probes which are used to plot a waveform. And we'll see that how that's used when we run the simulation. Okay. So, and the gate drive logic is here, which you have seen before. And then we have got this simple type 1 amplifier, which is, this is an integrator. The transfer function for this is simply 1 by SRC, and you can also write it down as 1 by S by, let's say, omega 0 or something, where omega 0 is your 1 by RC. Okay, so this is basically a unity, you can say, integrator. That's all it does. R comp and C comp are the only values which matter, and those are RC. And then of course the same is true for exact same circuit for the ST, except that now we're using a 15-volt voltage source to run the operations to indicate that it is not an ideal component, it's actual device. Now we have a simulation profile here, and this is, we're running transient analysis. We can run DC sweep, AC sweep, bias point, but here we're running a transient analysis, and we have set the runtime to 20 milliseconds. We start collecting data after 6 milliseconds. And the maximum time step is 5 microseconds. So again, our switching frequency is 50. So our maximum time step we allow is 5 microseconds. Configuration file, here basically you include all the text files. So all the text files you've seen, we included in the simulation. And so it's the file from ST, it's the triangular PWM file, this is the 3-phase BLDC parameter file, ideal switch, and the diode. And now this is where you can mess around with options when you have convergence issues. So you can play with relative accuracy of voltage and currents, which is 1 milliohms, 1 millivolt here or 1 milliamp here. The best accuracy of voltages, 1 microvolts. Best accuracy of currents, 1 pico. Best accuracy of charges. Minimum conductance for any branch, DC and bias blind iteration limit, DC and bias best case iteration limit, transient time point iteration limit, and then default nominal temperature, right? Now, of course, that doesn't do much for conversions. So normally we play with this parameter up here, relative voltage 1, 2, 3, 4, 5. So we'll mess with these 5 parameters. ITL1 normally is changed to 400, and then ITL4 is normally changed to 200 when we run into convergence issues. Hopefully we will not run into any convergence issues during our demonstration. And then you also have an option of changing the algorithm. So if you look at advanced options, simulation algorithm you can change. You basically have 0 or 1. Default 0, 1. Essentially you have the three options. But I don't think there's a difference between default and 0. Because as far as I know, there are only 2 algorithms used by PSpice. Newton-Raphson, and then the modified Newton-Raphson method. So that's, and then data collection, you can set all the 5 loads, but you can say voltage, currents, power, collect data on all nodes. Then you can also set it up so that you mark all the points and say collect data only where the probe is, right? So, so you can say at markers only, which will dramatically reduce your data file. Okay. Let's see, and then digital and noise. And then the probe window is where it will show the result. And we can see that you can set this up also. You can see display probe window when profile is opened, display probe window after simulation is completed. You can also do during simulation. That time the simulation becomes very slow because it has to display results while it's simulating. And then you can also see show all markers, on open schematic, last plot, or nothing. Right? So let's go ahead and simulate this. I think now you're pretty familiar with the circuit. You know all the components. So let's see if it will run. So this is the button we press for PSpice. Alright, so this was the last plot I had done. Well, I guess it's still not 29%. So this is 29%. So I think, so you can see this computer is a little bit slower than five. We're done. All right, so let's, I'm actually going to delete all this and close these windows. These ones. And we're going to actually, okay, let's see. Window, new window. All right, so let's see what should we plot. All right. I guess we have got markers at the current feedback and at the PWM output. So that's what I think it's going to show. So we have got, let's look at, so this is the voltage at the output of PWM. So PWM pulses essentially look like this. So the voltage signal is from 0 to 5 volt. That's what we have set. And we have a clamp here, which is, I think, this pattern you see is 1/6 the rotational frequency. Because the error amplified output just clamps to 1 or 0.99, where you have got So we can zoom in. So we can go say 6 milliseconds to let's say 7 milliseconds. So we can look at the signal. I can turn off the grid, or I can actually make this. So that's your PWM signal, and you can scroll down to see how it is behaving. Looks pretty uniform, pretty regular. And then let's go ahead and let's look at PWM AT. So I can either grab a probe and stick it here, and this is my top side PWM signal. Okay, does that make sense? And then I can look at also the bottom side. Now the bottom side I can also take from a trace, add trace, and I can just put V. I think let's see if it works. VAB, because we named the node as VAB. So that's your bottom side. Now, there's a difference in level. This guy is almost 3.5 volts, and this guy is 5 volts. And the difference is because we're using that AND gate, which internally limits the output to 3.5 volts. That's why it's actually good to eliminate that AND gate altogether. But it doesn't matter for the system performance. So, and then we can also look at the currents. So let's see here. So we can open up a new window, and I can either add, because I think it's IL1, which is the motor inductance. That's your motor current. And I can also add phase 2. I can add another plot and say trace add IL2. I can also change the color of this. And then another trace. Or I can also add another plot and add, let's say, IL3. Okay. Now we can also look at the. There is this facility in PSpice, which is the cursor. So let's say if I want to now this particular SEL is a selected, means this is the particular waveform or plot is selected, and if I want to click here, it will select this one, and if I toggle, if I use the cursor, then I can begin to read the values. So here you have values, you can see here. Now this one here, the particular top numbers are for the other window, so just pay attention to the bottom as it changes. So you can see if I go to 8 milliseconds, I have about almost zero current. So 185 milli, right? So just pay attention to this number here, these two numbers. And then the negative current is minus 6 amps. Okay. So let's see, and I can then turn it off. And anything else we want to see on this? Do we want to change the reference? This was reference 2, and we can definitely change it and see what happens. You can see output power, which is, now the way to do that, you can also define one function within SPICE which will multiply voltages and currents and give you power output. Right? We haven't done that in this one, but we have other demonstration where we show that. Here, we have to do the hard way, where we say, give us the power of W, V1, V2, V3, V4, V5, V6. So that's how we can also plot power. Okay. So I can try. This is a power probe. You have to be on the grid, otherwise it doesn't work. Sometimes it's a problem with PSpice. Let me turn the grid on. Let's see if I can look up this page. Rotate it. I guess it's for the device.
Remove the resistance on the other side.
Yeah. Yeah, I think that it's not giving me the power I'm looking
Maybe
for.
if you want to touch the same, you go to the this end. This one of the second.
This one?
It's not this side. The other side of the resistor. It should be the same one. Stick on the resistor itself.
So on and so forth. So that's the way to calculate power, but that's not the best way. Okay. DC component. Let's see here. It's about 78 watts. Right. So I can mark this.